Recording in progress.
Okay, good afternoon, everyone. So we're very happy today to have Professor Ilya Kuprov from the University of Southampton, who's going to tell us about optimal control of magnetic resonance systems.
Thank you. It's a great pleasure to be here on ASIP's invitation. We both worked in the same area of magnetic resonance for at least a decade now, admiring each other's work. You guys are lucky to have acquired him here. I've given two talks. Well, I'm about to give the second one. The first one in the morning was an educational one about what spin fundamentally is. And today we'll take a look at the recent work, particularly from my group, on how to precisely control spin systems, which are, of course, quantum mechanical dynamic systems, and how that is all used in practical magnetic resonance spectroscopy and imaging. So first, a reminder for the physicists around, of course, those who have been in the first lecture don't need this reminder about what is spin. It all started in 1922 when Stern and Gerlach discovered quantization of magnetic moment. If you send a beam of silver atoms through a magnetic field gradient, it splits. And if you turn the gradient on, it no longer splits. They concluded that magnetic moment is quantized. Then get Smith in 1926 suggested actual spin, and here we are in 2023, where it's an indispensable part of our daily work. And of course, spin is an elementary magnetic moment. All magnetic phenomena in matter are ultimately boiled down to spin. And it starts with elementary particles like electrons and quarks, who all couple between themselves and have extraorbital degrees of freedom that eventually contributes to spins of non-elementary particles like protons and nuclei. But ultimately, the reason spin exists is in special relativity. We have relativistic space-time boost operators whose commutators are actually rotations, and so there are more ways to rotate things in Minkowski space-time than there had been in R3, and so the rotational invariants are modified, and we no longer have just angular momentum, it's angular momentum plus spin. So there are orbital degrees of freedom, and there's an extra space-time contribution which is responsible for spin, and that's the Casimir invariant of the Lorentz group, which is conserved in special relativity. Of course, spin dynamics is a very rich topic. We have our great important cash cow called magnetic resonance imaging, where carefully introduced magnetic field gradients allow you to look inside objects without cutting them open. There's nuclear magnetic resonance, a standard tool in synthetic organic chemistry, where chemists do not do anything until they've made sure that the NMR spectrum looks right. There's an older brother called electron spin resonance that works on electron spin, and the more exotic things, magnetochemistry and magnetobiology. Turns out that certain organisms can sense the Earth's magnetic field and use it for navigation, and that's another long story about how they sense it. But essentially, fundamental reason here why spin exists is that relativistic boosts convert into rotations, and so we have the extra contribution in the conservation mode. Now, for those of you who are physicists or mathematicians, a bit of introduction would not hurt. The information content of magnetic resonance is quite extraordinary. This is a typical two-dimensional spectrum. You're looking at a matrix from the top. And these diagonal peaks that we have are specific to the local chemistry. The position of this line is determined by what's around a particular nucleus chemically. And these off-diagonal peaks, they correspond to interatomic distances, or the nuclei that carry spin. And as you can already guess, pretty much the entirety of information about the chemical structural topology and then how it is packed in 3 dimensions is already contained here, and skilled chemists, by just staring at it for a few minutes, would be able to sketch you a 3-dimensional structure of that pretty quickly. And for us, decoherence is actually an essential source of information, because decoherence in such systems is distance dependent. For those of you who do quantum technology, it's your worst enemy. For us, it is actually a very useful phenomenon which we can quantify and use for structure determination. Magnetic resonance industry is giant. Even in 2014, it was predicted to be in the billions of dollars. Every serious chemistry department has at least 5 instruments in the basement somewhere. Every serious hospital, of course, has several MRI machines. And again, the industry is in the billions of pounds. There are tens of thousands of instruments at research organizations and more at food companies and pharmaceutical companies and such like. Academic papers in the tens of thousands. For NMR, the statistics is slightly bigger than for MRI because the instruments are cheaper, but the capitalization of the major vendors of MRI devices exceeds the GDP of most countries. This is because of Siemens, General Electric, and transnational giants like that. Photosynthesis, for example, involves generation of spin-correlated radical pairs, so essential biological processes. I've already mentioned the birds and anything that is serious about magnetic processes in matter, one way or another. All right, when we are modeling this, how do we proceed? Firstly, all our models are time domain. So unlike electronic structure theory, for example, where we are mostly interested in the ground state and response properties, we need to run forward in time for a very, very long while compared to the time scale of our interactions, typically for many seconds. So we collect system, instrument, and experiment parameters. We build the Hamiltonian in a computer. We exponentiate it to find the thermal equilibrium. This is nearly always non-trivial. We use dynamical information that we have to generate relaxation superoperators. It depends on the statistics of the bus that we are coupled to. We thermalize the relaxation superoperator so it drives us to the correct thermodynamic equilibrium. We exponentiate the Hamiltonian and the relaxation superoperator to get the time propagator, make sure it drives us to the correct spot. We obtain the system trajectory and we project out the variables of interest. So this is extremely high accuracy time domain quantum dynamics with the requirement to have the correct phase after several thousands and sometimes several million periods of evolution under the Hamiltonian. So really stringent computational accuracy. And with good software, typically it's just this, and the rest can be subcontracted to the package of your choice. Right, so how, before we start controlling it, how do we do time domain quantum mechanics? Let's say that's our wave function and that is our Hamiltonian, time dependent. Then an infinitesimal increment in time is this famous exponential solution. Is you have this tiny time slice matrix exponential acting on your wave function, and that moves you forward in time by an infinitesimal amount dt. Of course, wave functions are not suitable for ensemble description because we have a gauge degree of freedom in quantum mechanics called the overall phase, which is technically present but doesn't include any observables. What it does mean is our averages over the ensembles vanish. And so we must make a contraption where the phase multipliers cancel. That's called the density matrix introduced by John von Neumann. And then if you substitute that here and do a few rounds of simplifications, you get this little von Neumann equation for what's called the density matrix. And it's just a glorified table of probabilities and correlation coefficients across the ensemble. And we sometimes introduce this commutation superoperator that simply denotes this commutator. Now, this Liouville equation is straightforwardly extended to dissipative dynamics. You just add an extra relaxation superoperator to chemical kinetics, to spatial motion, to whatever else that you have. This is really well developed, nearly 100 years of work on this by now. Thermodynamic equilibrium is just inherited straight from the Boltzmann law. You exponentiate the Hamiltonian and divide by the partition function. And in computer science parlance, it's inconvenient to drag a matrix around. Here, we usually vectorize it and then do appropriate stretch and squeeze transformations on the Hamiltonians to have a vector representation of all of them. So this is all known as the Liouville space. And so our vectorized density matrix evolves forward in time in a Schrödinger-like equation. So mathematically, this is a triviality. This is really well trodden. The hard part is the compute, because matrix dimensions here are sort of large. Okay, so how do people control quantum systems? Well, the optimal control in general, of course, predates quantum mechanics. And the problem consists in bringing any dynamical system from state A to state B with the maximum accuracy, with the minimum expenditure of time and effort, whatever it is that you define as your accuracy target, subject to whatever constraints or wishes you might have on the consumption of the relevant resources. And of course, famously, right, Van-Tragen's maximum principle and such are used to land spacecraft on distant worlds, where the task of landing with maximum accuracy and minimal expenditure of fuel is an optimal control property. But practically what we do is we create a system model. We expose some user-controllable parameters, electromagnetic fields in the case of magnetic resonance spectroscopy, and we optimize these parameter sequences or steering controls of our spacecraft until we reach the optimum that is required, and those are called optimal controls. And there's a wonderful review here in the quantum context. This is always invariably referred to as training Schrödinger's cat to do what he wanted to do. And this has rich background, in particular in magnetic resonance. Those of you who do just about any kind of quantum dynamics and spectroscopy will have heard about composite pulses that were originally introduced into magnetic resonance by Malcolm Levitt and Ray Freeman, who have realized that certain trajectories on the Bloch sphere, and of course Bloch sphere is just an abstract representation of SU2, the moment you have a two-level system, you have a Bloch sphere, that certain trajectories can be stabilized in the presence of certain stray interactions and also errors in the control processes by stacking the pulses together. So if you stack a number of rotations and look at the trajectory in the Bloch sphere, it turns out that the resulting trajectory is stable to a certain mathematically quantifiable degree to errors in the durations and amplitudes of these pulses. These are called composite pulses, and to this day they're used all over magnetic resonance, particularly in the imaging. So you can control things robustly on the Bloch sphere, but of course then magnetic resonance people have really made a fine art out of this piecewise defined and continuous and otherwise specified highly resilient control sequences that allow us to modify spin states of molecules with extraordinary precision and push the magnetization where we want it to go. And of course, a lot of modern quantum technology, sometimes with and sometimes without acknowledgement, is the carbon copy of this mathematics that was introduced in magnetic resonance. And then, of course, these Hamiltonians in the rotating frame are piecewise constant, so you simply have a stack of propagators that you are multiplying into a wave function density matrix, one after the other. Over to 1990s, Gaussian cascades, so the pulses need to be piecewise constant in situations where we need to accomplish highly accurate manipulations. So that is a haircomb of NMR signals, and say we need to invert one of them extremely precisely. These fine gentlemen have introduced a different class of pulses, which allow us to do selective inversion, selective excitation, and so on. And these, in their case, were combinations of Gaussians, but of course, in general, they're arbitrary functions. Those were early days. And they've also treated them as piecewise constant at the simulation level, but with fine enough discretization, you can get away with that. Okay, so in general, how would we think about setting up a quantum control problem for something that obeys Schrödinger's equation? Well, we would observe that there's a part of our Hamiltonian which we cannot control. In NMR context, these would be chemical shifts, J couplings, hyperfine couplings, and all such intrinsic molecular properties that we have no power over. Once we have our molecule, tough luck, it's the way it is. But then there is the part of the Hamiltonian which we can control. We can introduce various electromagnetic fields at radio frequency, microwave, whatever it is that you have. And this is instrumentally adjustable. What in particular it is, for example, currents through our coils times the corresponding Zeeman interaction operators. And so we can expand our control Hamiltonian as some adjustable control coefficients, which we can alter, times some control operators. So these are conventional controls, and these are control channels. Then we need to decide what we mean by optimal. Well, we want to arrive at our destination, so we start at some initial state. That's a time-ordered exponential propagator, so the most general possible solution to Schrödinger type equation, and that's our target state. If we hit our target, then this inner product is going to be large. If we miss our target, this is going to be small. So, for example, maximizing the real part of it with respect to this control coefficients is one way. But then, of course, there will be penalties, more practically sample heating and the availability of radio frequency and microwave power. As Asif would be able to tell you, it's singularly difficult to generate microwaves at certain frequencies. And of course, human body is salty. And whenever you have magnetic fields that are time dependent, they come accompanied by electric fields. Electric fields jitter the ions in your body and heat you up. The last thing you'd want to do is cook your patient. And so, of course, these things are pretty serious. We have these penalty functions. But so the objective, plus or minus the penalty, is our total cost functional, which we would like to maximize as a functional of these control coefficients subject to the external restraints. And a common way of doing that is to discretize time. Once again, the exact expression is this. It's the Dyson time-ordered exponential, but it can be represented in discrete time approximately by a series of time slices times this delta t. Sufficiently small delta t, the difference is insignificant. And that's called a time step or time slice propagator. And then, of course, once we've got these coefficients, that's just a bunch of numbers. We can simply optimize with respect to them. And the early work in this area used the simplest things they could think of, and that is the simplex optimizer, right? Just a polygonal node reflection of a primitive polygon in the space of high dimension. That works, but it's very, very slow, right? That's the principal problem with it. The pro side is you don't need to differentiate all the horrible mathematics with respect to your control coefficient, but we'll get to that. And there's no guarantee of convergence. So after some initial experimentation with this in the early 90s, people have abandoned it. So only for noisy and desperate cases, for example, if you're trying to optimize a running spectrometer that is subject to noise. Pretty much revolutionary method that is the current state of the art in quantum control was invented by Gaussian group, specifically Navin Kaneja in 2005. It's not dissimilar to backpropagation training of neural networks, but essentially we slice our Hamiltonian and we adjust amplitudes of slices by calculating gradients and stepping in the right direction. It turns out, and that's Navin's principal innovation, that the gradient can be computed extremely efficiently. So let's say this is our figure of merit. That's our initial density matrix. That's the bunch of propagators for each slice. That's the destination state that we would like, and we would like to maximize this subject perhaps to some penalties present. So initial condition, slice propagators, target state, fidelity must be maximized. Okay, what is each propagator? Well, it's the exponential of the evolution generator, which contains the parts we cannot control, conventionally called drift. And here I switched to Liouvilleans because these things can be dissipative, not necessarily unitary. And then our control operators and control coefficients and the delta t. So if we are calculating the gradient of this, well, if we take the derivative of that with respect to one of these coefficients, we need the derivative of the matrix exponential. So there it is, but only one of these exponentials depends on each individual coefficient. So what we need to do is we need to evolve forward from the source up to the point where that occurs, evolve backward from the destination up to a point where that occurs, and take an inner product across with this derivative. And this is extremely efficient. You need one calculation forward, one calculation backward, and one collection of relatively cheap inner products. So you get a gradient with respect to every adjustable parameter you have in the system at the constant cost of just two simulations. Really, really cheap. This is also the reason why neural networks are so easy to train, because you evolve forward, you evolve backward, and you basically use chain rule to calculate the entire gradient in just two sweeps. So, but notice that this setup is essentially piecewise constant, right? You have to set it up like that and then run with it. And there are many interesting practical considerations there. Of course, what we have in magnetic resonance is always either a radio frequency coil or a microwave resonator, in practice mathematically isomorphous to some kind of RLC circuit. And what RLC circuits do, they have response functions, right? So there are distortions. And if you solve the equations of motion for a typical RLC circuit, you get your standard first year engineering response function in the Laplace of Fourier transform. And so if you send a particular radio frequency signal, it's very rapid oscillations that look like solid blocks. In the heterodyne frame at the carrier frequency, it has the real and the imaginary component. And if you send that through the response function simulation, you can see the waveform is significantly distorted. And this is what you have in the heterodyne. And so practically, when we do the instrumental work, we need to take into account all of these distortions that come from the presence of the quality factors in these RLC circuits. There are various mathematical delicacies there about the condition number of this transform and so on. Okay, so how can we improve on that? And this is something that we have started doing a few years ago. Let's take a few steps back. Remember our setup was essentially piecewise constant. And in order to improve it, I need to take a step back and remind you of the definition of Riemann integral in basic undergraduate calculus. Remember, we were calculating the area under the curve, and we just split it up into blocks and we added up the blocks. Of course, now in quantum mechanics, we don't add up these slices, we multiply them up. And so it's not a Riemann integral, it's something mathematicians call the product integral. But of course, just as it had been the case for Riemann, a piecewise constant approximation to this is in some sense the worst one possible. There are much better ways of integrating the sum and by extension, and those are very recent, the Lie methods, much better ways to calculate the product integral. So this is how Mr. Riemann had that. And so what we have instead is Lie equation. This is how Sophus Lie invented Lie groups. He was considering equations of this general type. And as you can see, Schrödinger equation and even Gross-Pitayevsky equation, for state-dependent solution generator, they all have this form. Now, that's in our notation in quantum mechanics, that's our evolution generator, that's our state vector, and that's the exponential action by the evolution generator on the state vector. And so, whereas Riemann had a sum of slices, we have a product of slices, time-ordered product, because the propagators at individual times need not compute. But once again, a limit of infinitesimally thin slices gives us Dyson's time-ordered exponential in the end. That is the definition of the product integral. And I might add a much better definition than the one Dyson had for the time-ordered exponential. If you look at how Dyson introduced it, it's an absolute raving for but introducing it as a limit of a product of infinitesimally thin slices makes a lot more physical sense. Okay, so we agree that piecewise constant approximation is inefficient. So how could people possibly improve it? Okay, so our time slicing by piecewise constant is the least possible least efficient way. But two of my favorite mathematicians, Ari Isoles, Fernando Casas, also Hans Munchausen, a few years ago introduced the following. They said, well, okay, we need to find the product equivalent of trapezium quadrature, Simpson quadrature, and so on. So they did it Lie algebraically by saying, well, okay, let's reformulate the problem so that the generator of the exponential action is time-dependent as a whole. And then let's find the equation of motion for the generator of this action, and then only approximate the Lie algebra level, but also always work with the exponential map that is unchanged. So we don't approximate the exponential map, we approximate the evolution generator. And it turned out that much better integrators exist at not much more expense in terms of compute. If we have left edge and right edge evolution generator in some interval, we only need to calculate an extra commutator, which is negligible really, because we need to exponentiate that matrix anyway. And even a fourth order Lie integrator, left midpoint and right point, still requires just one extra commutator. And so when we implemented that, I had it somewhere. No, not in this talk. This is fundamentally more efficient because you need much fewer time slices, much like you need much fewer time slices in Simpson integrator compared to the piecewise constant integrator in the Riemann case. And another important thing, now that we can be, for example, piecewise linear, we have much less of a problem in the hardware response, because there are no sharp transients in here. Instead of being piecewise constant with vertical cliffs that generate strong instrument transients and therefore distortions, you can see the distortions here are actually quite moderate. The axis is somewhat differently scaled. You can see that the distortion is not big. The complication, of course, is we need to redo the GRAPE method completely. When Navin, Stefan, and others introduced GRAPE, they assumed the Hamiltonian is piecewise constant. But now, if we have piecewise linear slices, we have one particular Hamiltonian here that is shared between the two slices. So it occurs in the slice that takes us from point 1 to point 2, but also in the slice that takes us from point 2 to point 3. So H2 is shared. So a lot of mathematics needs to be done, but of course that's just the product rule. Individual propagated derivatives we know how to calculate, and so that turned out to be straightforward. So the next problem, okay, is how do you calculate the derivatives of the matrix exponential? One could do it by just differentiating a Taylor series, and this first order approximation is used in Navin's original paper. Turns out you sometimes need further terms in there, and so we tried summing it up to machine precision, and it resulted in significant improvement in situations when delta t is large. Or you can just finite difference it, but finally we found in the literature, Charles van Loon did that for matrix calculus, a nearly mystical equation. If you put two evolution generators on a block diagonal and the control operator on the block off diagonal and exponentiate the whole thing, then the required derivative mysteriously pops up in the corner. This is a highly non-trivial equation that takes a lot of Lie theory to prove, but this is the best ever way of computing matrix exponential, because you just need to exponentiate another very, very sparse matrix, and then you magically have the requisite derivative in the corner. Okay, so as soon as we've got cheap gradients, of course, we can do gradient descent. And doing gradient descent these days is a bit silly because, of course, people have long worked out ways of estimating the Hessian matrix from the history of gradients. And these quasi-Newton methods are a lot more efficient. So we can do full Newton-Raphson, but then we would need the Hessian, so the matrix of second derivatives. The convergence would be seriously fast, but this matrix is expensive, and of course its inverse might not exist. So there are various regularization approaches to that. So very rapid quadratic convergence, but very expensive. So that's a simple function in 2 dimensions. Gradient descent takes 63 evaluations to get there. Newton-Raphson takes only 6, but Hessian is super expensive. So quasi-Newton methods use previously calculated gradients to estimate the Hessian. And it turns out you don't really need exact local curvature. The sufficient thing to have is an estimate of the local curvature, and then you have an asymptotically quadratic convergence at much reduced computational cost because you're not calculating several derivatives there. So that's an example. Again, gradient descent 63 evaluations, Newton-Raphson 6 evaluations, quasi-Newton using Broyden-Petrikov-Arpchana formula. This one, 16 evaluations, right? A lot fewer than 63. That is a cost of just keeping the previous gradients in memory. So this is the current state of the art that is implemented, to my knowledge, in every package that uses GRAPE algorithm for quantum optimal control of just about anything. And then there are various regularization methods around computing second derivatives should you choose to do that. And that's an example of convergence. That's the steepest descent optimization, really slow, not recommended. That's the Newton-Raphson, super expensive, but goes straight into the floor. And these are various variations of GFGS, and this is the current recommended and implemented method. It's very sensitive to the accuracy of your gradients, so any approximations to the derivatives of matrix exponentials stagnate. You really have to converge your exponential derivative to machine precision, and this is something that we have now properly implemented in the Spinach package that we have for this. So another advantage of this GRAPE process is it's highly parallel and GPU friendly, and is, as I said, current state of the art. Okay, so how do we scale this to various nasty situations? Remember, we have spin systems. And the complexity scaling, if you're not careful, is exponential, right? The matrix dimension goes as 2 to the n, Liouvillean dimension goes as 4 to the n, 10 spins and game over, even if you're using sparse matrices and GPUs. So one particular thing to avoid is actually computing these exponentials. Turns out, much like there are many methods that compute matrix inverse times the vector without inverting the matrix, there are many methods that compute matrix exponential times the vector without ever computing the matrix exponential itself, which will of course be very memory intensive. Even if the Hamiltonian is sparse, the exponential usually fills up and becomes a full matrix, and so you run out of memory. So how do we calculate this without computing the exponential?
Can I ask you a question?
Yes.
I'm kind of confused. Is delta t now still infinitesimal, or is it now finite?
Your choice.
And if it's infinitesimal, then the exponential is just...
It's 1 minus IL dt. Yeah.
So I think I got lost a few slides back. I should have asked them when you introduced this GRAPE method. You suddenly said, oh, let's assume that we're just dealing with x of omega of t. But isn't that doing away then with the time dependency? Now we're just looking at global exponentials after all that are not Dyson series.
In this case, yeah, it's implicitly dependent on time, and you assume that your slice is thin enough that you are still approximating it well, or you are using Lie integrators that do take that into account.
But in any case, we're no longer looking at, are we at Dyson series here, at time order products.
Well,
that's
just one slice, and then of course in a different slice this would be a different matrix, and so you still have to multiply.
All right, but if it's just one slice, then I can assume delta t is tiny and just
you cannot always assume it, practically because your hardware has finite time resolution. So in a typical, say, MRI instrument, the quality factor of the coil may be such that you cannot afford to take slices shorter than perhaps a microsecond. And your carrier frequency for typical Zeeman interaction would be in the hundreds of megahertz. So in that case, delta t is not small, and it's not small because the hardware doesn't permit you to make it small. So there are external factors why that might be the case from the instrumental point of view. Anyway, so we have, I mean, it doesn't really matter what is here, call it A. We have an exponential times a vector. How do we compute it without computing the exponential? Right? There are methods called Krylov methods where you repeatedly act on the vector with powers of the matrix. And of course, here you do not need to take the powers of the matrix. You can just repeatedly multiply it into a vector, which is much cheaper. And it stands to reason, right? These are just the parts of the Taylor series expansion that the linear combination of this gives you the action in question. So what people do is they take this, they orthogonalize the subspace spanned by these vectors, project the problem into that subspace, take the exponential action inside this smaller subspace, and then project it back. Turns out this is an extremely efficient way of calculating that. Interestingly, General Alexei Krylov was a Russian Imperial Navy general, rather remote from mathematics. And interestingly, he survived the Russian Communist Revolution and retained his post mysteriously and life. So quite how he managed, nobody knows. But one way actually to further simplify the method is to observe that in fact we already know the coefficients with which to combine these, and they're just the Taylor coefficients. And so we simply reorder the multiplications. This implied cubic scaling of the matrix dimension of the complexity of calculating this. Here, if we have scaled our time step well, it's only matrix vector multiplications and a finite number of them. So if the L delta T has eigenvalues within the unit circle, then this converges monotonically to machine precision in about 17 iterations. So instead of order n cubed, you have some coefficient times order n squared, and that is significantly cheaper, particularly since L is usually very sparse and the exponential isn't. And so Anu in my group further generalized the general and extended this matrix exponential times vector to those problems where the generator might depend on time even inside the interval. So these Lie methods can also be reordered so as to avoid matrix-matrix multiplications and matrix exponentiation completely. So in version 2.7 of Spinach, these algorithms are all the default. And then there are various instrument-specific things that we might wish to enforce. Some instruments cannot output discrete sequences, they can only output specific functions. And so you must seek for an optimal solution on the set of coefficients in the basis set that you are given. Then, of course, it's just a chain rule. So d fidelity by d coefficient is d fidelity by the waveform times the matrix that contains all of those functions in its rows. And likewise for the second derivatives. So there's an extra option in Spinach that simply says, okay, wave basis, sine waves, take 30 waves, discretize them in 200 time steps. So then it's only 30 coefficients to vary rather than the original 200. That's an example of a solution where you've got a bunch of sinusoids. So you can see the resulting waveforms on 6 different channels are clearly sinusoidal. Then, of course, in any realistic experiment, magnetic resonance or spectroscopic or whatever, there are usually events that precede your pulse and there are events that follow your pulse. So there's a prefix and there's a suffix on your initial condition and the destination state. Thankfully, the prefix and the suffix do not depend on the control sequence, so we simply take that product and take that product and nothing else is changed. So the user can supply a function handle for the prefix, the suffix, and the dead time as a special case of a suffix. Sometimes, because of finite switching time of radio frequency and microwave electronics, there's an unavoidable time that you need to wait for the ringing to die down in radio frequency circuits before you can switch from transmit to detect. And so these dead times are also important. And we may want to go through specific subspaces at some point during your pulse. You may wish to be in a specific location or a specific subspace, in which point simply putting a projector into that subspace here suffices. The maximum of that automatically ensures that the system passes through this subspace, so the projector enforces that. And we call that keyholes, and those can again be passed as function handles to the software. That's an example of a 3-spin problem where we move magnetization from spin 1 to spin 3, I think. And the problem is set up so as to have a pure double quantum coherence at this particular point. So you see all the other populations are going to 0, and it passes through this keyhole that we have specified. Then technical things like we may want to freeze parts of the waveform, and again, this is straightforwardly compatible with the formalism and the software. We may wish to impose phase cycles. We have certain symmetries in the physics that the instrument does not follow if it has artifacts. So if artifacts transform by a differently reducible representation of whatever group we have, we can cancel them out by cycling through the fully symmetric irrep. This is called a phase cycle in spectroscopy. So that's again just repeating the calculation several times with different phases and combining them, straightforward to implement. And we did that. The book came out actually in 2023, where all of that is described. Finally, everything's parallelizable. Of course, you never have a single system. You might have a distribution in magnetic fields. You might have a distribution in local radio frequency amplitudes. There may be distribution of interactions in different molecules in your system, distribution of initial conditions, distribution of transmitter offsets, in which case it's just a giant sum of all fidelities that you need to simultaneously optimize, and it's automatically parallelized over all of such distributions. For example, if you specify multiple power levels, it will do it simultaneously to all of those power levels, and output you a fidelity distribution across whatever ensemble parameter you specify. As you can see, these pulses can sometimes look very complicated. And in case where you specify multiple distributions, it will plot you a surface, and if there are more than 2 distributions, it will plot you a histogram over the fidelity in your ensemble. Then, of course, it's sometimes necessary to start slow and to end slow, in which case as an envelope. You can treat it as a constraint on the amplitude and impose, for example, a spill-out penalty. Whatever's outside this envelope gets penalized, or you can simply just translate the waveform into the corresponding coordinate system and have an analytical envelope. Again, this is straightforward calculus that I will not bore you with. All of that is implemented and usable. There's an interesting generalization of composite pulse that again Stefan Glaser's group came up with. It is usually rather hard. Imagine you have your initial condition, that's your desired destination, and that is some imperfection, right? Or dirt. Suppressing this dirt can be difficult. You might, need too much power. You might need too much time. You might need too much time resolution. So completely removing this might be unrealistic. But flipping its sign is actually easier, right? And so why don't we carry a number of experiments in which we design such pulses that this remains the same, but this changes sign and then adds them up. These are called inter-scan cooperative pulses. And after a lot of algebra, you get a similar gradient of fidelity that you need to maximize. And you have a distribution of systems across the ensemble. Then you have multiple runs with different pulses that generate these imperfections with different phase. And if you add them up, these add up constructively, these add up destructively. And so that's a generalization of a phase cycle of inter-scan cooperative pulses. Finally, I'm coming to an end. This is a serious problem here, and this is a public relations problem that we have in this area. Even though this is a highly optimal pulse that is resilient to just about anything you can find in a typical magnetic resonance system, it's a nearly perfect high bandwidth inversion pulse. It's very difficult to convince your typical chemist that this bunch of noise is optimal with respect to anything. They're used to seeing smooth, interpretable waveforms. This is neither smooth nor interpretable, and in fact, if you look at the block sphere dynamics, it's another pile of rubbish. It's just this rubbish is mysteriously stable to just about everything that can go wrong in the system. And so how do we convince chemists, and that has proven to be surprisingly difficult, to start using this instead of their beautiful composite and shaped pulses? Well, what we need to do is stop trying to interpret the pulse itself and start interpreting the dynamics under that pulse. So let's say we have full Liouville state space, and we can partition it into some physically meaningful subspaces and then examine the populations of those subspaces. And this could be order of spin correlation, order of coherence, and other things that partition your typical Hilbert space, and then just take the norm of the projection into it and plot that as a function of time. Turns out that is phenomenally more interpretable. So that's a phase modulated pulse, again, with completely uninterpretable phase. But if you plot it in terms of correlation order dynamics, turns out you have a single spin state that fades, a two-spin correlation arises. So we have an entangled state here, and three-spin correlation, so tripartite dynamics kicks in and then fades. We are left with bipartite dynamics, and after the end of the pulse, closer to the end of the pulse, once the magnetization has been moved to the destination spin, we are again in the unipartite case. So you can see this nice and smooth and interpretable trajectory compared to the original pulse that we cannot interpret. And our sort of view on this is, I'm British, and so we see this a lot in spring. So the spin systems, the ensemble is like a herd of sheep, which you need to move from one place in the field to another. And of course, every ship has a different velocity, a different temperament, a different response. But this shepherd dog is quite skilled, actually. It runs around, a bark here and a bite there, and keeps the ship in a nice wave packet. And they are getting translated through the field where they need to be. And so that's the trajectory of the dog. And of course, if you consider the dog in isolation from what it's doing, the trajectory would be utterly incomprehensible. Right? But then if you look at the sheep are actually being steered quite precisely by that dog. And so let me give you a more complicated example. If we want to move magnetization from this proton to this carbon-13 in this little piece of a protein, then we have three dogs. One is the proton channel radio frequency, the other is carbon channel, the other is nitrogen channel, and the 6 control channels show chaotic looking dynamics. So trajectories of these dogs taken in isolation from what is happening in the system are uninterpretable. However, if you look at the dynamics, the magnetization of the proton, this H alpha, smoothly fades, gives way to the C alpha, so this carbon-13, which also smoothly fades as the magnetization is moved through the J coupling on what biologists call the CO carbon. And then if you look at it in terms of the correlation orders, single partite state fades, gives way to bipartite, tripartite, and 4-spin correlations are also appearing transiently. And then after a certain amount of dynamics, so somewhere here, we are back to the 1-spin state that corresponds to pure longitudinal magnetization of this carbon-13. So the interpretation problem for optimal control turns out to be not about the control sequences, but about the system dynamics. If we focus on dynamics and partition it into appropriate subspaces, then we see extremely tightly controlled dynamics, even though the original control sequences would not suggest that that's the case. Okay, so summary, there's a library called Spinach, which incorporates everything that I have talked about. It does every kind of magnetic resonance there is, these green and new things that just appeared there. So everything about NMR, everything I've talked about in optimal control, all types of hyperpolarization, most types of MRI, electron spin resonance, all sorts of generalities to do with group theory and Liouville spaces and Fokker-Planck equations, you know, all of the infrastructure that goes into there. And we are implementing or have implemented various exotica like DMRG, like tensor structure formats, where the system is too big for Kronecker products to be opened, various visualization tools, and so on. So this is open source and MATLAB, downloadable from spindynamics.org. I think we've spent pretty much 16 or 17 years now programming this, so it covers pretty much everything there is in magnetic resonance. And that's me. Thank you for your attention.
Any questions for Ilya?
No. So this is very impressive, and your analogy at the end was really, it made a lot of sense. So one of the problems we know with optimal control is implementation on hardware. So is it possible to consider minimum number of changes in the propagator so that we reach still the optimal
Yes,
state?
this is called optimal time problem. There is no analytical solution predictably. The practical solution is twofold. One, you can increase the duration and the number of slices until you are happy with the terminal fidelity of the optimization that you have. The other is to find some initial guess and then vary the width of the slices. That is also a straightforward and instrumentally often preferable solution, because once you've got some experiment to run, varying the duration of the slices is typically the easiest thing to do, because you don't need to recalibrate, reset, restart, so on. So yes, the problem only has a numerical solution. There is no analytical ones, but you can target optimal time, optimal slice duration, and other such things to minimize the instrumental distortions. The distortions themselves are pretty hard to model. I've showed you basic RLC circuit distortion, but of course in a real NMR probe, the inductance is distributed, the resistance is distributed, the capacitance is distributed, and you would need serious full-scale time domain electromagnetic modeling, which would be probe specific to actually find the true response function. And there's all sorts of cabling and amplifiers and so on even before that. So I'd say the best bet for a real NMR instrument is to measure it off. Stick a little antenna that is off resonance with what you're doing, record them, do a matrix pseudo inverse for the kernel of that transformation that distorts your waveform, and then see what happens.
Okay.
Other questions?
Yes, sir. Thank you for this very general introduction. Actually, I was intrigued by the statement of yours concerning the fact that you don't want to boil the patient in MRI. Well, this in principle is true, because in principle, yes, if you use gradients, and of course, if in the body of a patient there are ions circulating, in principle, of course, you can get, yes, you can transfer energy, you can heat up, let's say. But as far as I remember, the type of energy that we are dealing with are really, really small. And the KT factor should be much, much more important.
It's not just gradients, right? So there are two things there: gradient pulses and radio frequency pulses. So the engineering constraint on the gradients is electromagnetic back pressure. If you run up the current in a coil of high inductance, the coil expands. And there are significant mechanical strains in it. So this is what in practice, as well as the maximum current you can achieve in a stable way, limits the amplitude of the pulse gradient. But what, and that can generate induction and create light flashes, but they are relatively harmless. They are relatively harmless. What is more problematic is the radio frequency radiation, because that is at 100 megahertz or thereabouts, and it's the radio frequency that causes the most significant heat. So there are very rigorous legal constraints on how much energy you're allowed to deposit into the patient per minute.
That's the reason why the typical MRI cannot be done at extremely high field, because that's you can. Otherwise, yes, that may be starting a problem. But usually, this kind of precautions are taken when you have to, let's say, irradiate regions that are poorly vascularized. That is the real problem for this type of situation.
Typically, a modern Siemens wouldn't even allow the user to exceed the limits. It dynamically calculates the power deposition, and the research instruments, you have to sign a significant amount of paperwork with Siemens if you want them to remove those constraints.
Thank you very much.
Thanks, Ilya. It was really nice talk. In the last slides, you showed the polarization transfer from this proton to carbon. I'm wondering, is there any experimental group tried to approach this using
Of
this?
course, I mean, that's been done a very long time ago. So optimal control pulses are now shipped as standard with Bruker instruments. I believe they're Burkhardt-Lewis pulses. They are ultra broadband inversion, ultra broadband excitation, various pulses with specific phase behavior. They are really becoming unavoidable because in the recent 1.2 gigahertz instruments, because of these power considerations, there are really vicious limits on the radio frequency power. And then it turns out to be impossible, for example, to have a hard carbon-13 pulse anymore. So to uniformly invert 200 ppm of carbon bandwidth on a 1.2 giga, you will not have sufficient RF, even in principle, to make it a hard or even a simple composite pulse. And in that case, if you want uniform inversion, optimal control is the only choice. And I understand that they are now just standard manufacturer supplied pulses.
Any other questions? So you used, I think in your Lie group method, you have a Lie group in the background. So what determines that Lie group?
It's the nature of quantum dynamics. If we have unitary dynamics, then that's a special unitary group, right? Some subgroup of SUN, where n is the number of energy levels. It's not often that the dynamics is perfectly unitary. It's usually dissipative, at which point the structure becomes that of a semi-group. But still, we have an algebra that is just a metric space of operators, and that is connected by the exponential map to the manifold of the underlying propagators. And it turns out that if you look at these super tight requirements, so imagine we're doing MRI, right? What you are seeing as brightness in MRI is the phase of the magnetization. So at the end of a very long and tightly orchestrated dynamics, in your simulation, you must have your phase correct. This is very stringent, right? For example, molecular dynamics, people cannot achieve that. So we need integrators that are accurate down to phase after maybe 1 million periods of Hamilton. This is really super tight. Right? And the only way to achieve such accuracy is to observe all the group theoretical constraints. If you use straightforward Runge-Kutta, for example, even like 8th order Runge-Kutta, you will see that the phase is lost nearly in right? 5 periods of the Hamiltonian, you get an erroneous state. So it was a discovery of the mathematicians who were originally working in celestial mechanics, where that is also a problem, so symplectic problems, who realized that the only way you can guarantee the correct phase at the end of this very long calculation is if you never disturb the propagator. So you can never fool with the exponential map that must stay. The only thing you're allowed to change is the generator of the evolution. And so, whereas Runge-Kutta approximates the propagator itself, these Lie methods always approximate the generator and are always exact when they're doing the exponential. So this Lie structure is super important because our accuracy requirements are so high.
Very interesting. Great. Excellent. Any other questions? Okay, if not, let's thank Ilya again for the very nice talk.